As promised, we'll now talk about how did I know to let u be the denominator and not the numerator? Well, there's a few strategies for picking u substitutions that work, and here they are. If the integrand involves a fraction, try letting u be the denominator. If the integrand involves an exponential expression, try letting u be the exponent. And that's what we did in example 1. If the integrand involves an expression raised to a power, try letting u be that expression. In other words, the base on the exponent. And last, if the integrand involves a radical, in other words, a root, like a square root or a cube root, try letting u be the thing inside the radical. Now, that word try is a little ominous. It implies that the u substitution won't always work, and unfortunately this is the case, and it's one of the things that makes integration difficult. You don't always know what's going to work. But how do you know if it has worked? What do I mean by the u substitution worked? Well, it's worked if all of the x's could be replaced by u's. And here's a cautionary note. We know that the integral of x dx is 1/2 x squared plus c. And similarly, the integral of u du would be 1/2 u squared plus c. But what about the integral of u dx or x du? Neither of these will be 1/2 x squared plus c or 1/2 u squared plus c, because the variables don't match. So we don't know what the integral of u with respect to x would be, and we don't know what the integral of x with respect to u would be. We just cannot have a mix of variables when we're integrating. We can only have one variable. And that's why I say the u substitution has worked if you're able to get only one variable inside your integrand. If you can get all the x's, including the dx, replaced with u's, including a du. I've got some more examples for you. Let's try finding the integral of x over 5x squared minus 4 dx. In the list of strategies we just talked about, the very first one was if the integrand is a fraction, try letting the u be the denominator. So let's let u be 5x squared minus 4. Then that means that du dx must be 10x. So if I multiply both sides of that expression by dx, I get that du is 10x dx. Now there is an x dx in the integral. All right, there's my x dx, but there's not a 10x dx. So right now, I need to do a little more work to figure out how I'm going to turn everything into u's. And the trick is, since I have this x dx in the integral, if I solve for that by dividing both sides by 10, I can see that 1/10 du is what would go in for x dx. So let's put in what we've got and see if there's any leftover x's we need to deal with. The x dx has turned into 1/10 du, and then the 5x squared minus 4 in the denominator is all swallowed up in the u. I'll bring the 1/10 out front, and the antiderivative for 1 over u du would be ln of the absolute value of u plus c, and we'll wind up by putting back in what u really is. U is just our name for 5x squared minus 4, so we change the u back into that, and we're finished. Let's try the next one. We want to find the antiderivative for 7 times the quantity 3x minus 1 times the quantity 3x squared minus 2x plus 4 to the 10th power. Boy, there's a lot of stuff going on in here. We've got things being multiplied. We've got a big old thing raised to the 10th power. If we consult our strategies for choosing a u substitution, we have this one that says if the integrand involves an expression raised to a power, try letting u be the expression. In other words, let u be the base under the exponent. That's what's going to help us here. Okay, so I'm going to let u be 3x squared minus 2x plus 4, because that's the base on the exponent 10. Then that means that du dx would be 6x minus 2. So du would be 6x minus 2 dx, if I multiply both sides by dx. Now, gosh, we don't see a 6x minus 2 anywhere in there. Let me put in what we've got so far. I've renamed the base on the 10 u, so I'm going to have u to the 10th, but everything else is x's, so we've got a mixture of u's and x's. If we can't fix that, we're stuck. We have to try a different u substitution. But let's notice over here where we said du equals 6x minus 2 dx, notice that we can factor a 2 out of those parentheses. So that's something to try. And, oh, this is actually helpful because I do have a 3x minus 1 in my integral. So 3x minus 1 times dx, that's almost what our du is, but my du, it's got that 3x minus 1 dx, but it's got this extra 2 in there. Well, just like we did in the last example, we can adjust for that by dividing both sides by 2, and then we get that 1/2 du is what we'll put in for 3x minus 1 dx. So let's do that. I'm going to bring that 7 out to the front. You can put the 1/2 out front right now if you want. Usually I would just stick it out front, but I know this is new to you guys, and I don't want to split up the different things that we're putting in so that you can't easily see what we put in for what. Okay, so I've got the 7 out front. The 3x minus 1 and the dx are all swallowed up in the 1/2 du, and then we have our u to the 10th power. So with that said, I'll now write what I would ordinarily actually jump right to, which is to have 7/2 out front, and then the antiderivative for u to the 10th du is going to be u to the 11th over 11, and then we have our plus c. So let's see, I have 7 over 22, and then times u to the 11th, but u was just my name for 3x squared minus 2x plus 4, so we need to put that back in. We have the 11 power and the plus c, and we're done with that one.